Okay, so this is a review. This is going to be the review of what we did Thursday and Friday. All right. So the first one is this introductory skate park. All right. And I added the pie chart as well as the bar graph. The grid shows how high, and the speed shows, of course, how fast. All right, let's make sure we're on the right one. We want to be on the introductory skateboard. Okay, and we want to be on the U. All right. Now, according to this, first we take this person up. We can take her to the height of 8, which is right here, correct? And so if you do that, then she just falls straight down. But if you put her like this at 8, then she hits that and slides off. And we can see that she goes off on the other side. All right. So then when we start again, we probably don't want to have to do this every time, do we? All right. So we pick her up. I put her at, what should I put her at? How about I put her at 6? All right, see how she's right at 6. See how she goes to 6 on the other side. Yeah. All right, and then let's watch what is happening. Let's watch what's happening to the height. So notice that she starts at 6 and she goes to 6. All right, and she continues going back and forth to 6, never losing any height. If we slow her at any point, so let's slow her right up here, we'll see that she has mostly blue as potential energy and a little bit of kinetic energy because she's at the top of the ramp. If we let her go to the bottom of the ramp, notice she has mostly the green kinetic energy, very little blue, and very little thermal energy. All right? And if we do this in slow motion, it might even make this easier. So let's put her up at the top. All right, she's right here. Notice that the circle above her head shows only potential energy. Now, when we say go, right here she has some of that potential energy has been turned into kinetic energy. All right, and then we let her go to the bottom, and we note right at the bottom, she only has kinetic energy. She's going the fastest she's ever going to go. And in fact, the speed at this is 10, 20, 30, 40, 55. 55 is her speed when she leaves the top at 6 meters high and comes down to the bottom. Remember, kinetic energy depends on her mass and depends on her velocity. So, since it's the same person all the time, the mass would be the same. All right, and then if we continue it, she has kinetic energy, and it's turning into potential energy. Look how it is. Already, 3/4 of it has turned into potential energy, and this is called transfer of energy. Energy is neither created nor destroyed. And as we keep going, when she gets to the top, notice we caught her almost at the top with only potential energy. All that speed she had at the bottom, she's now at 0, just about at 0 speed, 0 kinetic energy. And most of it is the height because, once again, she's very close to 6 meters. All right, and we saw that no matter where we put her, all right, so let's put her at 4. All right, we got her at 4. Only potential energy, and then when we start her, she goes down to the bottom, and now it's only kinetic energy. She's going the fastest which is at 10, 20, 30, 45, and from 4. All right, and then we let her go. She goes up to this far. Her speed is decreased. She's not going as fast as she's climbing uphill. And notice that most of the 3/4 of the kinetic energy has been transferred already to potential energy of height. Remember how she left at 4. So she's only going to go as far up as 4 before she starts going down again and back up to 4. And remember, her major speed, her highest speed was 45. At 6, it was 55. All right, so let's reset this skater at, we want her to be at 2. All right, are you ready? She's only going to go as high as 2, isn't she? And her greatest speed is going to be 10, 20, 32. 32. So when she starts at a lower height, she not only goes to a lower amount over here, the same height that she left, but she's also going at a slower speed. And down here, it's all kinetic energy. As she continues up, eventually all the kinetic energy has been converted to potential energy of height. And down here, when we let her achieve that and then come down again, she's her fastest. And then at this point, all the kinetic energy has been transferred again to potential energy of height. She has the potential energy that when we let her go, we know all of that is going to turn into kinetic energy. And right here, all kinetic energy except for that tiny little thing where she's beginning to transfer some of the kinetic energy into potential. All right, so let's go over here and look at this now, and let me just make it as big as I can. All right, so, whoops, that's not what I wanted to do. Let me push this over here. This is what I want to do, make this as big as possible. All right. So, now that we've done that, and we know it has to do with her on the ramp, let's make this really big, all right? So, the scenario, when you pick up the skater and let her go, her, should say, potential energy increases due to the height, all right? So, 6 meters is the height. Potential energy is mgh, the mass of the skater, times the acceleration due to gravity, which is called g, and h is the height. All right, what do you notice about energy if you lift the skateboard up to 2 meters? Well, all the energy is potential to begin with. When the skater is at 0, all the energy on the graph is kinetic. The highest speed was about 29, only we got 32, didn't we, when we were doing it? What if you place her at 4? Well, it's higher than 2 because the transfer is higher in speed. Remember, the speed was 45, and that was the maximum. All right? And she returns to a height of 4 meters on the other side. All right, and there's no friction. What if you place her at a height of 6? Well, that's higher because her height is 6, so the mass and g are the same. So there's a higher kinetic energy transferred when we saw she had a speed of 55. So the greater the potential energy, the greater the kinetic energy as shown by speed, by a higher speed, this time of 55. And when the skater was at the middle, there is a similar amount of PE and KE in the middle of the ramp. All right, so some has transferred and about half So the kinetic energy is half the kinetic energy as was present at the bottom of the ramp. All right. Now, it says, explain at what point is the speed the highest on the U-shaped track. Well, we measured it at the bottom, the bottom of the U. The speed is highest at the bottom, 55, when the skater began at 6 meters at the bottom, and before the skater starts going up the ramp again. At that point, the kinetic energy is transferred to potential energy as she moves up. Now remember, I'm going fast, but you can stop the video at any point to have me explain it or go back and do that, whatever is necessary. So at what point is the speed the slowest? Well, it's always the slowest at the top of the ramp just before it starts down again, because isn't it 0 at that point when it changes direction? Look at your total energy as the skater moves back and forth. What's the pattern? Well, the total energy is always the same. The total is the sum of all the KE and the PE. If it's all KE, then it's more KE. If it's all potential energy, then it's more potential energy. But the sums of kinetic energy and potential energy will always add up to be the same unless there's friction. And that's what we will do in the next simulation. Without friction, what do you notice about the heights of the right and left? Well, did you notice that if she left at 6, she went up to 6 on the other side? Left at 4, got up to 4 on the other side, etc.? Yeah, it's the same height. So clearly we're not used to this. We must live in a world of friction. With any of the heights listed above, does the skater fly off the ramp? Well, if it was greater than 6, we saw the skater fly off the ramp, didn't we? From your observations, once she begins down the hill, explain whether she will ever stop. I think we saw no matter how long we let it go. If she starts at 6, she goes to 6 on the other side, then she falls back down and goes to 6 on the right, falls back down, goes to 6 on the left. So without friction, the skater will never stop. Now we know for sure we don't live in a frictionless world, right? All right. The greater the height, the greater the speed. Why is that true? Why is that true? Think about it. As we've discussed these energy types, what would be a rational, scientific way to explain what has just happened? Well, at a greater height, there's more gravitational potential energy, right? So therefore, when all the potential energy is transferred to kinetic energy, the kinetic energy can only be as high as the potential energy was to begin with. Since KE depends, thank you, since KE depends on the mass and G, the acceleration due to gravity and the height, then the reason is that higher potential energy means higher speed. We're always using the same skater's mass and the same gravitational field strength, so only the height affects the skater's speed. And all that height of potential energy was transferred into speed. All right? All right. Now, the last one, we get to actually change this so that we are looking at friction, because we've now realized that what we're used to with motion must have to do with friction. All right. Now we can thank Isaac Newton for thinking about that for us, because he was so clever. He realized, what if we didn't have friction? What would happen? So he imagined if you rolled a ball, since there was no friction to stop it, it would just keep rolling on forever. If you went down the ramp and there was no friction, it would go on forever, just like we showed, right? Up to 6, down, speed it up to 6 on the other side. That's what he realized what would happen naturally. But there is friction in our world, and friction is a force that opposes motion. All right, so here's an example. When a car slows down, it's because the brake on each tire generates friction, right? And the friction is between the brake pad that you push down onto the tire. Secondly, have you ever noticed that cars need a force to keep going because there's friction between the tires and the road, right? Have you ever felt a tire after you've gone somewhere? They're really hot. And why is that? We know that friction causes energy to be dissipated just into heat. The word dissipate means much, much less. Dissipation also has another connotation, which is bad, that it's not good to be dissipated. Yes, we've lost that energy then as heat, right? And it heats up our environment, but we can't ever get it back to make it useful. So we think of frictional heat as unuseful form of energy. If you were using it to heat your house, that would be better, wouldn't it? But we can't ever get this heat from the tire to heat our house. They're not connected, are they? So some of the kinetic energy of motion has to be converted to heat, and that's what friction does. It opposes the motion. And the thermal energy that is transferred from kinetic energy is just heat. Objects slow down because some of their kinetic energy has been converted to heat. On a skateboard, friction between the wheels and the ramp surface slow the skater down. So if you have a really, really good skating ramp, well then somebody's polished it so that all the little holes in the concrete don't slow you down. But normally, the wheels will hit all the little surfaces in the concrete, and that interaction between the various little heights, where it's not perfectly one height, that will be transferred into heat because of the force of friction. All right, so the simulation shows you how significant the force of friction really is. Wait till you see it. No energy is lost. The kinetic energy is just converted to heat energy. All right, so we're going to go to Friction Skate Park. Let's see if I can pull up that simulation. All right, I think this is it. We want to have the grid, right, to show the heights. Let's do the pie chart because that's so helpful. And then we'll look and see if the speed is the same as it was before from the various heights we let her off from. I put the friction in the middle of the scale, and her mass has just stayed in the center like it was last time. All right, let's do slow motion. Let's lift her up to 6. Oh, no, let's lift her up to 8. Let's lift her up to 8. All right, on 8, she went off the ramp before, right? Let's see what happens now. Here she comes. She didn't fly off the ramp. She started at 8, but didn't fly off the ramp at 6. And now look what's happening. Every time she goes up and down, now she's only coming back at less than 4. Now she's only coming back. Do you think it's going to be about 2? This is pitiful. Yes, we can see friction is really ruining her ride. Yeah, and not only that, as we watch her, we can tell there's a point at which she's going to have 0 speed, 0 kinetic energy, no potential energy because she's at the bottom. So what are we going to find? All the energy, potential, kinetic, has been converted to heat. Look at this point. So she's at the bottom with no potential energy, and she's still, so she has no kinetic energy. But is the energy lost? The answer is no, the energy isn't lost. It's all turned into heat energy. The unfortunate part, though, is we can't use that heat energy for anything else. It's just dissipated into the air around the skateboarder's ramp. All right, that was at 8. Let's restart her. Let's put her at 6. All right, now we expected her to go 55 miles an hour. Remember that? Or whatever it is. It's not miles per hour. All right, here we go. Here she comes. Down the ramp. She got to 4. She comes back up, but she doesn't even go to 4. Now she's coming back down, and she only gets to 2. Now she's coming back down. This is pitiful. Once again, you can see she's not happy about this because she realizes she's going to come to a stop. This is not going to go on forever. She's going to come to a stop. And at the bottom, she has no potential energy. And when she stopped, she has no kinetic energy. And we're seeing that all those energies have been transferred to thermal energy or heat. All right. So I think you get the gist of this. If we start at 2, you know what will happen, don't you? So they aren't getting to nearly the speed. At 4, we didn't even see what speed she went to, did we? We thought it should be 45. So let's restart her at 4 and see what we got, because I forgot to look. All right, here she goes. Right at the bottom. Oops. 10, 20, 35. Not 45, only 35. Her speed was only 35 of whatever these units are. So the speed decreased with friction as well. All right, now let's go back and answer these questions about friction. All right, we took her to 8 meters, remember? And we thought she should fly off the ramp, but she didn't. She didn't go off the edge like before when she didn't have friction. So friction changes everything. So the friction not only has lowered the total energy of kinetic plus potential, there's none anymore. All the energy has been transferred to heat. All right, at 6 meters, we saw the same thing. She never reaches 6. The friction transfers kinetic energy and potential energy to heat. She ends up at the bottom of the ramp and no speed. All right, so the same is true. So I wanted you to look again. We didn't look at the thermal energy bar graphs because I didn't think they were as clear as the pie chart was. So let's look at these. This first one, there's potential energy, and that makes up all the energy. The total is the same. So this must be before the skater starts down the ramp, because there's only potential energy, and that makes up all the energy. Here, though, the second one, there is kinetic energy, and there's a similar amount of thermal energy. So the total is kinetic plus thermal. Where would this be? This would be like halfway up the ramp on the other side. Yeah, halfway up the ramp on the other side. And then here we have only kinetic energy. This is the highest amount, but only small bits of PE and thermal energy are there. So this means it must be close to the bottom of the ramp, because there's so little potential energy due to height, so it must be at the bottom, right? And the maximum kinetic energy is at the bottom. All right, and now we have mostly kinetic, but we actually have some potential, and all these and tiny bit of thermal added up. So there's mostly KE and a significant amount of PE. I think this indicates the skater has left the height, gotten almost halfway down. Notice the friction has only caused a small amount of thermal energy so far. All right. Now, with friction, present, what's happened. These are the conclusion questions. We've said that you realized we lived in a friction-full world when you saw the idealized version of the skater on the ramp coming up to exactly the same height on the other side and going on forever. So I want you to answer these questions about how the friction affects the height of the return. How does the friction affect the final motions? With friction, will the motion of the skateboarder end or keep on going? By the end of the motion, what's the proportion of thermal energy to potential and kinetic? And what's the total energy at any point? All right. So this is what you should be able to answer after doing the simulations by yourself and now with me as we've gone through them again. So how does the potential energy affect it? All right, let's go. How does the friction affect the height of the return? Well, the return is significantly lower than the start side, right? Yes. How does friction affect the final motions? Well, everything we see is slowed. That doesn't make sense. Let's try that again. The kinetic energy is smaller because the speed is slower. That is because friction is stealing some of the kinetic energy. Notice the skater continues to slow down. With friction, what will the motion be at the end? Well, we saw at the end the skater was stopped in place at the bottom of the ramp. So clearly, she doesn't keep going. By the end of the motion with friction, what's the proportion of thermal energy? Well, all the kinetic and potential energy has been converted to thermal energy, which is heat, right? Oh, so all the energy at the end is thermal. What is the total energy at any point? Well, no matter where we looked, the total energy was the total energy all right, just a second. The total energy is the sum of KE, PE, and thermal energy. The thermal energy is the major proportion near the end of the motion. Right. All right. So, I think you know what that word says. So, we have finished all of this. Now, I hope you understood it between going through it yourself the first time and now us going through it a second time. This was more complex. All right, so I'm sorry that I'm not there, but I know that you are able to figure this out. when you do it on your own, and then when I go back and explain it so you see what it was you didn't understand. All right? All right, I hope you have a great day, and I will talk to you later. Bye.